Hi folks, welcome back to Physics with Captain Rod. We're going to take a look at number 25 in your Unit 4 homework. So let's see what we got going on. Whoops, I need my pen on here. Alright, so we have this system here, which is released from rest. Now if we kind of observe what's going to happen here, this animal is going to start accelerating down. This animal is going to start accelerating up. The pulley is going to have an angular acceleration. So this one is another problem that is just screaming work energy methods, right? So let me give these names. Let's call this one A, this one B, and this one P for pulley. Position 1 looks like this. Redraw the system at position 2. Right, mass B will be up here. Mass A will be down here. And write out the work energy theorem. I told you you'd be writing this down a lot. And we're not done yet. All right. Let's put the datum at the floor again. Now, PE1. This animal has a potential energy at position 1. But B doesn't because B is at the ground. The pulley technically has a PE1 term, but the pulley is not changing in potential energy. If something's not changing in potential energy, you can ignore it. So don't worry about the potential energy for the pulley. Right? So hopefully now that'll get you through this. System started from rest. Okay, PE2. Let's talk about that. Position 2, mass B is now up here, and it has a potential energy, so you have to take that into account. Mass A is down here at the datum. Right, so that should tell you what to do there. So PE2 now should be done. We've talked about that. All right, let's talk about the KE2. So again, at position 2, mass B is moving, so it gets a kinetic energy, 1/2 mv squared. Mass A is also moving, so it gets a kinetic energy, 1/2 mv squared. But the pulley is also rotating, so it gets a kinetic energy, 1/2 I omega squared. Now, as we kind of read through the problem here, let's see. We have the radius of the pulley, but not its mass, I don't believe. So we can't calculate this right now. We can't yet get that, right? So keep in mind that's an unknown in that work energy equation. Just keep that in mind. Oh, and then let's chat about the work term. So the work term, again, it's all about how you define our system. Let me do this in orange. If we defined our system as just mass B, the tension is an external force that would be adding energy to mass B and would need to be included. If we define our system like this, the tension also is an external force, and we would need to include it in a work term. But if we define our system like this, the tension, in effect, is not adding energy or taking away energy from the system. And by the way, I said tension singular. There's actually 2 different tensions in this problem, because the mass of the pulley is going to affect the problem. The tension on the left and the tension on the right are different values. And we'll talk about this more in class, but for now I will just state this, that neither tension on either side are adding energy to or taking energy away from this system, so you don't need to include work terms for them. There's also an external force at the pin, right here, right there. Because if there wasn't, the pin would fall down. But we don't need to worry about that one either, not because it's internal, but because it's not moving, the pin isn't going anywhere. So there's no work term for that force. So long story short, this term is 0 for this problem. So get this all written out, and you should have 3 kinetic energy terms, 1 for A, 1 for B, 1 for the pulley. The unknown in the problem is hidden in the KE for the pulley, the 1/2 I omega squared. Now, in that equation, if you look it over, you should have 2 unknown velocities. Well, you should have 2 velocities, one at A and one at B. But if you look at the geometry of this problem, these are going to be equal. If A moves a foot, B also has to move a foot in the same time. And then you should have an angular speed as well. Okay? And I'll kind of go through this again. I believe in going over it over and over and over. I'll do this in yellow. If you look at this yellow picture that I just drew, right, that distance along that path is your arc length, S. And it's equal, through the definition of the radian, equal to R times the change in theta. And if you divide by time, the S becomes a V. And the change in theta becomes an angular speed. Right? So hopefully the yellow is showing up okay in the video. So you're going to use this to get rid of this in that work energy theorem. Okay. So now your only unknown in that equation should be a V that we don't know and the I, the moment of inertia. Okay, now we can start talking about what do we do about that. All right, this object moved 3 meters in 4 seconds. You can take the 3 meters and divide by the 4 seconds, and that's going to give you 0.75 meters per second. But it's important to realize what you just calculated. That is the average velocity over the time interval where A moved this distance. And in the work energy theorem, the KE2, you need the instantaneous velocity at 2. So if you're having trouble with that, ask and I'll help you out. I'll just leave it there for now. I will tell you that the 3/4, the 0.75 meter per second, is not the correct velocity to use for the KE2 term. There's one more step you have to go through to get that final velocity. So anyway, that will hopefully get you through 25. I hope that this helps. Have a great day.